All right. So thank you, Dr. Hall, for joining us today. Dr. Hall is a full professor in the Department of Computer Science and Mathematics at Université de Quebec in Chicoutimi since 2010 and is the current holder of the Canada Research Chair on Software Specification, Testing, and Verification. He earned his PhD from Université de Quebec in Montreal and has been a postdoctoral research fellow at University of California. Both an ACM and IEEE senior member, Professor Hall has won multiple awards and international conferences for his research on software testing and formal methods. The team he leads it's a French Laboratoire d'Informatique Formelle, has produced a number of free software tools that directly apply the research of his results. In addition to the BeepBeep event stream processing engine, let us mention CornyPickle, an automated testing tool for web interfaces, and LabPal, an environment for streamlining the execution of computer experiments and their inclusion within research papers. Over a career spanning 15 years, he has authored more than 100 scientific publications, which, according to Google Scholar, has been cited close to 600 times in the past 5 years. Professor Hall has earned a reputation for his fun and lively presentations, which I can attest to, at international events over the years. You can have a look at some of the slide decks from past talks on his SlideShare page, which I'll put in the description of this recording. Over to you.
Okay, well, thank you for this introduction. So it's nice to meet you for this presentation. Actually, the presentation I'm going to give today is a new version of a tutorial I first gave in a conference many years ago. And I'm glad to have this opportunity to refresh the material and to have a new presentation that takes into account the many years of research that I've done on the topic of event stream processing. So, so yes, first of all, maybe we should start with the simple question. Oh yes, I should share my screen. It would be a bit better. Sorry about that. There you go. Okay, so event stream processing with BeepBeep3. So BeepBeep3 is the name of a library that we developed in our research lab over the course of many years. And I'm going to give you an overview of how it works and what you can do with it in the next couple of minutes. But before even looking into how BeepBeep operates, maybe it would be interesting to first ask a very simple question, which is, what is an event? And in its broadest sense, an event can be taken as any unit of data that is produced by the execution or the observation of a system. And you can see on my slide that I put the word system between quotes because what counts as a system can be very broad. Here I gave some examples of what events could be. For example, if you have a bunch of sensors in an apartment or in an environment, well, these sensors periodically produce units of measurement of something, let's say temperature or pressure or some lights or something like that. So each of these readings by an individual sensor could be taken as an event on which you might want to perform some calculations later on. If you're considering, for example, the feed of stock information about stocks from the stock market, then you could have, for example, the update of a stock price. You could take this as an event. And of course, inside this event, you could have multiple elements of data. You could have, for example, the price of the stock, whether it's the opening or the closing price of the stock. So each of these data elements could be taken as an event. If you look at, for example, a log that is recorded by a web server, then each line of this log corresponds to a user requesting a particular resource on a website, for example, a user visiting a web page. And then you record all sorts of information about these requests. You have the time. You also have the URL, so the link of the page. You may have the return code that the server produced for this request, for example, 404 if the resource doesn't exist, and so on. So each of these things, again, could be seen as possible events in a system. I did some research on the debugging and testing of video games. And in a video game, you also have lots of events happening. For example, if you periodically take a snapshot of the game's state at various moments in its execution, then there's a ton of information that you can collect about this internal state. For example, the exact location in the game world of various characters. You might have information about which level is being played, how many lives the player has, how much time has elapsed since the last snapshot or since the beginning of the execution. So again, you can periodically produce snapshots of the execution of the game and take all of these things as separate events. You could consider parcels being delivered. So every time something happens to a parcel, it gets picked up, put into a truck, or delivered, or put into a delivery center. So every time these things happen, you might want to record the progression of the parcel all the way to its destination. And so all these data elements, so what is the ID of the parcel, what is the date it's expected to be delivered, who is the last person who manipulated this parcel, these could all be seen as events as well. And one last example, you can even look at a chess game and take every move that is being done during the game as a possible event. So this event would tell you what is exactly the piece that is being moved from what position to what position, how much time has elapsed since the player played their last move, and so on. So as you can see, and I could give many other examples of what events could be, but you can see that the definition is pretty large. Then the other question is, what is an event stream? And an event stream in its simplest way is just an ordered sequence of events of a given type. So you could have, for example, a sequence of temperature readings, or a sequence of chess moves, or a sequence of URLs that are being requested by visitors on a website, a sequence of timestamps of things happening. So everything could be seen as event streams of a specific type. If you take this stream and you save it for later use, the object that this produces is often called a log. So you have stream when you are in a kind of real-time setting, and the same data, when it is stored for later use, is often called a log. And then, of course, you must not forget that events can be composite. So a single event can contain multiple data elements. So for example, a temperature reading and a location and a timestamp and all sorts of things. So events don't have to be like primitive elementary values. They can be composed of larger data structures. And then event stream processing is just a calculation that we do on an event stream. For example, if you have a stream of temperature readings, you might want to ask, what is the maximum temperature of the last 100 readings? In the parcel delivery scenario, you could ask something like, who is the employee who delivered the most parcels, let's say in the last month or in the last week? In the case of a web server log, you could look at the navigation habits of users and ask something like, is there a user who accessed page A from page B? In the stock market scenario, you could evaluate, for example, patterns or trends in the evolution of a stock price and ask a question like, has a specific stock decreased in value 3 days in a row? In the video game setting, you could ask something like, have we seen in the level the player colliding with an enemy during a jump while the character is in the air? And in the case of chess games, you could analyze a bunch of chess games and then ask questions like, what is the move taken most frequently after the opening move e2, e4? So all these things, you might say that they look like database queries in a way, because we're asking questions on data. The difference with stream processing is that we are often concerned with the order of occurrence of the things. And I highlighted in yellow some of the elements that are related to the ordering. For example, page A from page B, it means that you must first visit page B and then visit page A. So the ordering in which you see things is important. So that's one important element that is often present in stream processing. And the other one is that the result is very often produced incrementally. Very often we are producing stream of events and we want to process them in real time as the events are being produced. And we want to calculate a result that we update every time we receive new events. So it's a process contrary to a database, which is more static, we could say, because you have this kind of fixed database and then you run a query, you get the result and you're done. In the case of stream processing, you have new data that is being produced. So new events that are being added to the stream, and then you're interested in updating the output, so updating the calculation that you do on this stream based on the new events that have been added to it. So it's something that very often happens in real time, and you want to update or increment on the previously calculated result. Then another question is, where do you store streams? Well, you can store streams depending on what they are. You could store them in a text file according to a specific format, let's say JSON or XML. You could store events in a spreadsheet. Actually, there are lots of activities that we do in a spreadsheet that could fit the definition of stream processing, because each line, let's say in our spreadsheet, corresponds to something that happens, and then we calculate averages or things like that over this data. So it's a primitive form of stream processing. You could say that events can be stored in a relational database. So it's a bit different from database queries, but there's nothing that prevents somebody using, let's say, a relational database to add lines to a table and see that as a form of stream. And of course, another possibility is that you just don't store them at all. If you're interested in processing these things and just getting the output of some calculation, you may just discard the original input stream and just keep the output. So there are situations where the original input streams are not even stored anywhere. They're just, calculations are being done on them on the fly, and then we just keep the result. Okay, so that was the introduction about what is event stream processing, and now we'll talk a bit more in detail about one possible tool that you can use to perform stream processing on event streams. So it's called BeepBeep. It is an open source library that we've written in our research lab since 2015, and it's written in Java, but actually it can be used to perform stream processing in any language that uses the Java virtual machine. So, for example, if you're used to writing things in Scala, you can use BeepBeep as a library in your Scala program. Same thing for Groovy, same thing for Kotlin, because they all rely on the Java virtual machine in the background. So I'll give a couple of examples of code later in this presentation. And the example in this presentation will be in Groovy, because I think it's one of the simplest. It allows to write very simple code compared to, for example, Java, which is much more verbose. If you want to use BeepBeep in your own projects, it's open source, so you can download it from GitHub. You can also just add it as a dependency. If you have a Maven project, it's also available on Maven Central. So just go on the URL that is shown on the slide, and you'll have more information about how to get BeepBeep, but it's completely free and open source. If you want to get help on how to use BeepBeep, there's a textbook that is available, and it's under an open access license. So of course you won't get a paper copy of the book if you download it, but at least it's completely available as a PDF. So again, you have the link to access that book if you want to read it. So BeepBeep over the years has been used in our research team in about 20 research papers that both describe BeepBeep or use BeepBeep to do something else, to solve another problem. We earned one Best Paper Award for this for one of these papers, and it's been downloaded about 1,000 times since it's been released, and we started counting the number of downloads. So if you want to use BeepBeep, you're not alone. There are resources. It's not just some obscure research library done in a university that is poorly documented. So there's a lot of effort that has been put into giving resources so that other people can use it without us. There's a couple of design principles behind the programming of BeepBeep. The first one is simplicity. So we wanted BeepBeep from the beginning to be very simple to use. So it's made of elementary building blocks, and as you will see, it requires zero configuration. There's no heavy setup of all sorts of things that you need to use BeepBeep. It's really easy to start using it. We also wanted it to be intuitive. So it relies on a very simple mental model. So when you write a calculation in BeepBeep, what happens is governed by very few rules of operation, and in general, what's happening under the hood is very, very close to what you think is happening, what you have in mind regarding the calculation that is being done. It's also flexible. So there's a principle that's called composition, which allows BeepBeep to be extended in many different ways. So we have dozens of extensions to perform specific tasks. And you can also design your own calculation units if you want. And finally, we wanted it to be lightweight. So we want to keep the library as small as possible, and we want it to be able to work under low system requirements, for example, embedded devices or a Raspberry Pi or something like that. So you definitely don't need a cluster to use BeepBeep. It can run on your desktop machine. It can perform light calculations directly on your computer. And actually, the core library is a jar file that is less than 300 kilobytes, and that's all you need to download to start using BeepBeep. So in the system, an event can be any object. So an event can be a number, it can be a Boolean value, it can be a character string or a tuple. So these are common things that we see in BeepBeep calculations, but it could also be a set or a function or a plot or a color or a chess move. Any Java object that you want can be put into a stream and then be processed by some BeepBeep calculation units. So you don't have, like in some other systems, the restriction that an event has to be a tuple, or it has to be a number, or it has to be a specific object. It can be anything that is a Java object can be an event in BeepBeep. Then we have a fundamental notion in BeepBeep that's called a processor. So a processor is a computation unit that just ingests input events and produces output events. So to this end, it has what we call pipes. So we have input pipes that are the endpoints that receive input events, and we have output pipes that are the inputs that produce output events. And that's as simple as that. Everything in BeepBeep is a processor that performs a different kind of calculation. That's of course the whole point. So we have some processors that have more than one input pipe, and we can also have processors that have more than one output pipe. So we have no restrictions over the number of inputs and outputs that a processor can have. We call a source a processor that has no input pipe. For example, QSource is, as we'll see a bit later, is a processor that produces events based on a queue that you define in the beginning of the program. You also have keyboard, so you can produce events and put them into a calculation based on what the user types, for example. So the events are created out of nowhere because it's the user who creates them by typing. And then we also have sinks, which is the opposite notion. Sinks are processors that have no output pipe. So QSync accumulates events in a queue. Print receives events and just prints them at the console. We even have black hole, which is a processor that takes events and just destroys them. And yes, it has uses in some situations. We tend to use color conventions to represent pipes of specific types. So you see here the colors that we generally use for some common types of events. And then, of course, nothing prevents a processor to have pipes with different types. So here you see an example at the bottom of the slide where you have one input pipe, which receives strings, while the other one receives numbers, and it produces as its output a tuple. So processors have total freedom in the types of events that they can receive and produce. What I'll talk about in the next couple of minutes is what I call the basic processors, which is a set of core processors that perform elementary operations on streams. Typically, when you have a calculation in BeepBeep, you will definitely use one of these somewhere in your calculation. So that's why I call them core processors, because they occur very, very often. Of course, in BeepBeep, there are many more processors than the about dozen that you see here. And please refer to the book if you want to know the whole set of processors that are available. But with these ones, you can already start to do interesting things on streams of events. The first one is what we call apply function. And as its name implies, we just apply a function to events of the input. So for example, here I have a processor that evaluates the square root. So it's parameterized by the function that it applies, which is square root in this case. And so you see that if I give an input stream on the left, it will produce the output stream that you see on the right. And we can indeed observe that 2 is the square root of 4, 9 is the square root of 3, and so on. Here's another example where this time the processor receives tuples as its input, which are key value pairs, sets of key value pairs. And the function it applies to these tuples is to get the value of attribute A from each tuple. And we can see that indeed, if we extract the value of A in the first tuple, we have lowercase a. If we extract the value of attribute A in the second tuple, we get lowercase b, and so on. This other example, we see that we have a binary function, but one of the arguments of this function is a constant. So it turns it into a unary function that receives only one argument. So here's a notational trick that we use. The diamond represents the first input pipe, and to its left we have constant 0. So constants are represented as rounded rectangles like that, like events. So what this processor does is to check whether each event is greater than 0. And of course, this returns true or false. So what you get as an output is a stream of Boolean values that are either true or false. So 4 is indeed greater than 0, so we get the value true. 0 is not greater than 0, so we see that the second output event is false, and so on. We also have processors with more than one input pipe, and we can apply a function to them in the same way. So here, addition is a function that has 2 arguments, and we have 2 input pipes. And what we will perform here is the pairwise addition of events at matching positions in both streams. So 8 is indeed 4 plus 4, 9 is 9 plus 0, 37 is 16 plus 21, and so on. And we can even have functions with 3 arguments. So this function here represents an if then else. So it will return the content of the second stream if the first stream is true, and otherwise it will return the contents of the third stream. So here we see that the output is lowercase a because the first stream is true. Then we have uppercase B because the first stream is false, and so on. So we just apply functions to events and we turn them into other events. Then we have this extreme case where we turn every event into the same constant. So here, for example, I have the processor that turns every input event into 0. So 0 here, 3 is turned into 0, 1 is turned into 0, 4 is turned into 0, and so on. I can also change the type when I'm doing this. So for example, here I have a stream of Boolean values, and I turn them into the character string made of character A. So yeah, that's turned into. And then we have decimate. So decimate removes events from the input stream. And the rule to remove them is we keep one event every n. And n can be, of course, any positive value. So here I parameterize my processor with value n equals 2. And I can see that the first event is output. Then the other one is skipped. Then the third event is output. The next one is skipped. Then I get the fifth event, and so on. So I indeed keep every other event from my input stream. There's trim that discards events, but this time it discards events from the start of a stream. So if I trim with n equals 3, it means that I will discard the first 3 events and I will output the other ones as they are. So here 1 in the output corresponds to the 4th event because I discarded the first 3, and then 5 is the one that comes after 1, and so on. There's fork, which is pretty easy. It just replicates the input stream into each output pipe. So I take an input stream and it becomes n copies of my output. So there's not much to say about this. There's filter, where we discard events from a stream based on a control signal. So filter receives 2 streams. The first one is made of Booleans, and the other one is the stream we want to filter. And so every event at a given position will be let out if the control signal is true, and otherwise it will be destroyed. So here we see that the first event is output because we have the value true in the control signal. The second one is skipped because we have value false. The third one is sent to the output, as is the 4th one. but then the other one is skipped because we have value false. Same thing with F, and then the last one is skipped. So the Boolean stream doesn't need to be related to the filtered stream. They can come from completely different sources, but of course, in many cases, what we calculate for the control signal is a condition on the stream we want to filter. But the way the processor is defined, it doesn't have to be like that. Accumulate applies a function and it accumulates the values. So it computes a kind of sum, but it's a symbolic sum because it can be something else than numbers. So for example, if I instantiate the accumulate processor with addition and the start value 0, then the first output will be the first input event plus the starting value, so 3 plus 0. Then the second output will be the second input event plus the last value, so 1 plus 3. And then I do the same thing. The third event is 4 plus 4. The fourth event is 1 plus 8, and so on. So what this processor does is to calculate the cumulative sum of all the events, all the input events that we've received so far. If I replace addition by max, the maximum function, then what I will calculate is, for example, here, the maximum between 3 and minus infinity, which is 3. Then the maximum between 1 and 3, which is 3. Then the maximum between 4 and 3, which is 4. So what we compute here is the maximum value we have seen in all events received so far. And then we can accumulate things that are not even numbers. So if I take, for example, logical disjunction with the start value false, so what this will produce as its output is something that could be translated into, have we seen the value true so far? We can also do calculations on sliding windows. So here I can run a processor on a window of n successive events, and that's what I produce as my output. So here my window is of width 3. So I take the first 3 events, I put it in the parameterized processor that I gave here, which is the cumulative sum, and I keep the last output, which is 8. Then I will do the same thing for the next window of 3 successive events. I output the last event that this calculation produces, and so on. So what I get here is actually the sum of 3 successive events as my output. So 8 is the sum of the first 3, 6 is the sum of 1 for 1, and so on. What I give for the calculation of a window can be any processor. We're not limited to aggregations or numerical inputs. So here, for example, I use disjunction on a window of 4 events. So what I get here as a calculation, if you look into the details, will be something that returns true if a window of 4 events contains at least one value true. And we'll see in examples a bit later how this can be used in real calculations. And then, of course, these processors are very simple, but the point is that if you want to do complex calculation, you do that through what we call composition, which means passing the output of a processor to the input of another. And so graphically, it means just drawing a pipe between the output of one and the input of another one. And by doing this, we create what we call processor chains or pipelines. So here's an example here where I give these 5 events as my input. I receive those 3 events as my output. And what do I get? Well, we could look at the details and realize that this is the square of every other number from the input. When we create pipelines, the pipelines are one way. So events always flow from outputs to inputs and never in the reverse direction. Any output can be connected to any input as long as they have the same type. And we have seen that we use color codes to represent types. So the point is that you just connect an input pipe and an output pipe of the same color. That's the trick to make sure that the typing discipline is being followed. And there are many types that can occur in the same pipeline, as you can see. There's a bunch of code examples of simple and not so simple pipelines that you can do with BeepBeep. Most of these examples come from the textbook, but you also have them in a separate repository that you can explore. And you see the URL here, because of course, because of time constraints, I will not be able to too many examples of pipelines, but you have more than 100 illustrated code examples that you can have a look online. Here's just one simple example. So maybe we could ask ourselves the question, what does this pipeline calculate? Well, we see that we have streams of numbers because of the colors of the pipes. And if we run the calculation on the simple stream made of these five input events here, we would see that what comes out of the processor as the top would be those 5 events, 3, 4, 6, 12, 15. And what would come as the output of the other processor at the bottom would be 1, 2, 3, 4, 5. And then we take those two streams and we perform the pairwise division of those two numbers. So what we get is 3 divided by 1, then 4 divided by 2, 6 divided by 3, and so on. And what we have at the top is the sum of all events that we've received so far. And what we have at the bottom is the number of events that we have received so far. And we divide the two things. So what we calculate is actually an average. And this is what we call the running average of the input stream. It's the average of all the numbers that we have received so far. Now, if I complexify my pipeline a little bit more like this, now what we have here is what's in the box is the same thing as the previous slide. It's the running average of the input stream. But now this thing here is given as a parameter to the window processor on a window of width 3. And so if I take these input events and I push them into this processor, what I will get as the output is what you can see on the right. And we could realize that we take a window of 3 successive events, and what we get out of them is their running average, is their average. So actually what we are calculating here is the average of each window of 3 successive events. Little more complex example here. There are a couple of symbols that we haven't had the time to study. But if we look at this pipeline, we could realize by knowing what the pictograms mean that first we read lines from a file. Then we split each line into a list of words. We output each word as an event. Then we create a slice or a kind of substream for each word. On each of these slides, we count the number of events that we received. We keep the last event, and this is our output. And what we get is actually a map, a table like this one, that corresponds to the number of occurrences of each word in a file. So this is the word count program, which in the field of big data is often seen as the kind of equivalent of Hello World for standard programming. So doing word count in a system is a way to illustrate how you do things with that system. So this is how you would write this pipeline in BeepBeep. I was talking about the slice processor. So slice is another very often used processor in BeepBeep, where you split an input stream into a substream according to a function, and then you run a processor on each substream. So suppose you have a situation where you have multiple players rolling a dice. So you have a sequence of events where you have player 1 rolling dice number 1, player 2 rolling the dice, getting 5, and so on. And what you want to do, for example, would be to say, let's split this into a stream for each player. So we would get now substreams that are separated like this. So the ordering of the events is still preserved, but now we have 3 substreams with only the events from 1 player. Now, suppose we have 2 functions to extract the contents of a dice event. So I give a dice event, and the first function gets me the name of the player, and the other function from the same event gets me the dice value. So suppose we have these 2 functions. Then I can write a pipeline like this one. So what I'll be doing is I'll be slicing for each player. So I'll create a substream for each player. And then for each of these players, I will get the dice value out of each event, and I will calculate the sum. So the output I will get is a map that will associate each slice and the last event produced by the processor instance. So in the first event, I get a map that says player 1, the total of the dice rolled is 1. Then after the second event, I get a map that says player 1 still has 1 and player 2 has now rolled 5. Now player 1 rolls again, so now the total is 5. Now player 3 appears in the map because it's the first event that concerns player 3, and so on. So what you get is a stream of tables associating each slice with the last event produced by the processor for that slice. So it's one of the most complex processors in BeepBeep, but it's very, very useful. So actually what we are counting here is the total of the dice rolled by each player. Here I have another example of a pipeline where this time I will slice for each dice value instead of slicing for each player. And then for each slice, I will get the name of the player, and I will accumulate these names into a set. So now the slices correspond to dice values instead of players. So I get the same events, but now they are distributed in slices in the way you see here. And you see at the bottom that what I will be calculating incrementally is the names of each player that rolled a dice with a specific value. So depending on how you define these processors, you can perform pretty complex calculations using very few boxes. Because of time constraints, I will have to skip this part about push versus pull mode, and I will go to the more interesting examples. So I'm sorry if I'm going very fast over these slides, but I prefer to go to the examples. Yes, one of the things though, yes, it might be a bit dizzying to see all that. One of the things I want to insist on is that I said that in BeepBeep there's a very simple mental model where what you think is happening is pretty much what is indeed happening under the hood. So the processors operate in a lockstep fashion. They consume input events one at a time. They produce output events one at a time. And it means that you can think about the way processors operate really like an animation, where here, for example, I ask a processor, do you have an output event to produce? Then it will turn upstream and say, well, do I have an input event I can consume? And then since it has two inputs in this case, it will query two different sources. Then it can perform its calculation and produce the output. And it always operates in a very, clockwork, lockstep manner. And how it's being programmed, how it's being implemented inside the library is exactly like what you're seeing here in the animation. Like everything proceeds step by step. Events are being queried, they are produced, they are relayed downstream, and that's exactly how each pipeline operates. Eventually, you might reach an end of stream signal that says, well, there's no more output event to produce, and then this signal can propagate in the pipeline. So a processor needs an event in each input pipe to execute a computation step. And when this is the case, it can produce an output event, or it can produce more than one output event, or nothing at all. So in some cases, the processor may decide just to not produce any output from the input it received. And otherwise, the incoming events are stored into internal buffers until they can be consumed. So for example, here, if I push events to the processor, always in the same pipe, but I push nothing in the other one, then those events that I push are not discarded. They are accumulated in a buffer until they can be consumed. So if eventually I push an event in the other pipe, now the processor will wake up and say, okay, now I have a pair of events and I can do something with them. Again, I will have to skip this example in push mode, but you get the idea. To write BeepBeep programs, what you do is, first of all, you instantiate processors, then you connect them, then you push or pull events, and that's about it. So if you want to run, to create programs using Groovy, what you need is Java 8 or higher and Groovy 4 or higher. Here's an example of a simple program that creates a BeepBeep pipeline. So first of all, you write these two lines, and this corresponds to step 0, which means you have to load BeepBeep. You have to tell the program you are going to use this library. And the nice thing about Groovy is that if this library is not loaded, it will take care of fetching it from Maven Central, install it locally, so you don't even have to do this step by yourself. Just writing this line grab here makes the thing install automatically. Then you instantiate processors. So we have classes for each processor. So here I create a new instance of count decimate, a new instance of apply function, a new instance of print. And then, of course, I need to connect these things if I want them to interact. So the last part is to write statements that are called connect. So I say connect DC to SQ and then connect SQ to PR. And then you just take this, save that into a text file. Let's call it squares.jvi. So JVI is the extension for Groovy programs. And that's it. However, this program does nothing because it's missing part 3, which is pushing and pulling events. And to do so, you can use 2 objects. The first one is called pushable, which is a reference to an input pipe that is used to push events. And the other one is pullable, which is a reference to an output pipe, and it's used to pull events from the exit. So here, suppose I want to use a pushable, so I use a method called getPushableInput. So I get a reference to the pushable, to the input pipe of DC in this case. And then I just do calls to push, method push on this object, and it will push events down the pipeline. And as you see here, the last element of my pipeline is something that will print the events it receives from its input. So if I now run this program at the command line, so what I need to do is just type Groovy with the name of my program, and I press enter, and I get, in this case, I will get this. And if you look at the output events that are being produced, they are exactly the ones that I've shown in my example when I presented this pipeline earlier in the presentation. So indeed, it does what it's supposed to do. It performs the correct calculation. So here's another more complex example of a pipeline that uses a fork, and it introduces a slight technical element here where if you have a processor with more than one input pipe or more than one output pipe, you need to specify the index. So that's why here we just don't say only connect A to B, but we have to say which output of A we want to connect to which input of B. So that's why you have these 2 numbers that appear in the call to connect. But otherwise, this program works in the same way as the one before. You can even, that's the fun thing in Groovy, you can even shorten these programs using a couple of syntactical shortcuts. For example, in Groovy, instead of writing connector.connectAB, you can just write A with this vertical bar B, and it will perform the same operation. And if I have indexes of inputs or outputs, I can use brackets to say connect this output to this input of processors A and B. And then this connective, this pipe connective, returns the last processor of the chain. So if I connect 2 things here, A to B and then B to C, and then I put C in my variable P, in Groovy, I can write P equals A pipe B pipe C, and it will produce exactly the same result. And finally, when I have pushable objects, I don't even need to obtain a reference to them explicitly. So instead of doing get pushable input followed by a call to push, I can just write what you see on the right. So this presents the potential of shortening the programs and making them maybe a bit more readable, less verbose. So instead of writing this, you could reduce that to this using all the syntactical shortcuts that I've shown you. So here's an example of Hello World. So how do you do Hello World in BeepBeep? Well, you instantiate a print and then you push Hello World into it, and that's it. That's going to print Hello World to the console. Okay, last part of this presentation, I will present 2 use cases showing examples of slightly more complex calculation that can be done using BeepBeep. The first one is interesting. It's a data file that's made of 2 million chess game summaries in a special notation called PGN, and you have an example of what PGN looks like on the right. So it's a text file that contains metadata about a particular chess game, followed by the list of moves of that particular game. So there exists on the internet a file that contains 2 million of these things in a single big text file. And the goal is to process this file to measure what we call first move advantage, which corresponds to the situation where you tend statistically to see more wins for white than for black because white starts in the game of chess, and that it gives an advantage to that player. So the goal is just to count the games according to each possible result. So 1-0 means a victory for white, 0-1 is the opposite, and then you have 1/2 that corresponds to a draw. So we can do this in BeepBeep. The possible pipeline to achieve this result is the one you see here. So we first read the file line by line, then we will retain only those that contain the line with the result. Then we will slice according to the content of this line. So one slice for each possible result. We turn each line into one and we sum, which means that we count the number of events that we receive in each slice. This is what we get here. We keep only the last event and we print it to the console. So if we run it on this big file, what we get as the output is this. And you see that you have the number of games that ended in each of the 4. Yeah, there's another weird result, which is star. But then you have the number of games that end in each of these possible results. And you do observe that there are more games for white than you have, more wins for white than you have wins for black. The interesting thing is that there's a person who did a program using a Hadoop cluster to process this file, which is 1.7 gigabytes. And it takes 26 minutes to calculate the result. If you run this BeepBeep pipeline I've shown you on a desktop computer, you will get the result in 35 seconds. And the point here is that, well, using a cluster depends on the size of the problem that you have. And here in this case, we are not in the case of a whale problem. It's not a huge problem. And it means that for the scale of this problem, using BeepBeep on a desktop computer is well enough for the job. So that's one important message I want to pass, is that sometimes when we talk about streams, we say, well, why don't you use a cluster? Why don't you use Apache Flink or Kafka? Well, there are situations where using a desktop computer and a library like BeepBeep is well enough for the job, and using the cluster is overkill and is actually counterproductive. And here's another example where this time you have an industrial robot moving on a shop floor, and it produces an event stream of its current state. So its state is made of its current position, two-dimensional position, x, y, and also its orientation, which is the angle. Let's say you can see this as the angle it has between it's the way it points and the north, let's say. So you have a stream of these values, and the goal is to detect skidding situations. So the robot is considered to skid when there is a large difference between its orientation and its motion. In other words, it's pointing in a way, but it's moving in a different way. You could see that, well, you could imagine this with your car during winter as well. So a possible pipeline would be something like this. So what we're doing here is that if I get a stream of robot events, what I get here is values for X. And then what I will do here is I will subtract a value with the previous one. So what I get here is the X distance traveled between two successive events. Now, okay, I unzoom, I have a larger pipeline. So what I'm doing here is, this is what we've seen in the previous slide. It's the delta X. Here is the same thing we're doing, but for Y. So we have the delta Y. And what comes out from the output is the angle. It's the angle taken by the displacement of the robot in a succession of two events. So it gives an angle and a kind of instantaneous orientation. And then I zoom out a bit more. And what I will do is I will compare the angle of this instantaneous orientation with the angle the robot is pointing to. So I get the absolute value of the difference between those two angles, and I get the difference between the angle of motion and where the robot is pointing to. And then I compare this and I evaluate if this thing is greater than some angular value k. So what I get here is something that will output the value true if this delta theta, which is the angular difference between the motion and the orientation, is greater than my threshold. Now I could say, well, an isolated skidding event, we could say, well, this might be a false alarm. So let's trigger something only when we have n successive events that are considered as skidding situations. So I take this pipeline and I add one more thing at the end, which is a window of a specific width. And I take the conjunction of all the Boolean values in this window. So this pipeline will output the value true, but this time if the difference, the angular difference, is greater than my threshold n times in a row for n successive events. So it's a way to refine here my alarm by saying, okay, I remove those single events, single skidding situations, and I raise an alarm only when I'm seeing this for long enough. Okay, so that was my second example, which brings me to the conclusion. So we've seen that event streams can be found in a variety of situations, and that processing them in real time does not always require a complex or a distributed setup. The example of the chess games, I think, was particularly telling in this respect. We've also seen that with the BeepBeep stream processing engine, we can perform a wide range of calculations on event streams. And of course, since you've seen me rush through my slides and skip a couple of sections in my presentation, you might get the idea that there is much more to say about stream processing than what could fit in this short tutorial. And I encourage you to go look at the documentation that is available online, maybe at some of the research papers that describe what we can do with the library. And if anything else, please do not hesitate to contact me if you have possible scenarios where you would like to use the library or extensions that you might want to have developed for the library. So thank you very much for your attention.
Thank you very much, Dr. Hall. This was a great presentation. I will ask our vast audience if they have any questions, or I'll ask a question myself.
Yep. I will go ahead with questions first. Firstly, thank you so much for this presentation. It really impressive. So I have just couple of questions to get things clear. When you were on the synchronous part, when you were showing the synchronization, then we were receiving two streams of the inputs as two different streams of the events as input. So what was you showed that, for example, on one input we are not receiving the input, and on the other input we are receiving the events, but it will be processed only when we will receive the event from the first one also. Then it will make use of the most recent event in the buffer and then just makes a computation. What if we don't want it we want to, we have some sort of system in which is synchronized based on the clock, and then we want to process input at every clock cycle. So, and if we don't have the input for one of the stream, then how this can be managed in such scenario?
Okay, so just to make sure I understand, so in that situation, what would happen in the way BeepBeep is implemented now is that if you have a clock cycle where the processor should produce an output, and let's say there's an input in only one of the two pipes, then in the way BeepBeep is implemented now, it will not produce anything as its output because it's missing another input. So if we still want the processor to produce something, maybe the last value that it produced at the previous clock cycle or something like that, then we would need to implement processors that work in what I will call semi-synchronous operation, because they still produce event at definite moments in time, but they may they may produce a value in situations where they don't have an input to consume on each of their input pipes. So it could be implemented. So it's not incompatible with the basic classes that are in BeepBeep, but at the moment, there is no processor in the core library that operates in such a way. So we would need to implement new versions of processors to allow this kind of behavior.
Thank you so much. And my second question was also about that. You showed some of the components there. So how difficult is to introduce a new component in there? For example, we find that this is some operation which we want to perform, but it is missing in the library. Then how difficult is it to introduce a new component there?
So there's the main class in the library. It's called synchronous processor, or there's even the parent of this, which is called processor. So if you want to implement a new functionality, you just create a new class that is a descendant of this one. And then there's a bunch of methods that you need to implement to do the processing. And then once you created that class, it can interact with any other processor that already exists in the library. And as a matter of fact, in the project where we use BeepBeep, it almost never happened that we didn't have to implement a new processor for some very specific operation. And so it's not a very complicated task. And if you go in the textbook, there is a section in one of the chapters that explains how to create your own processor to do something very customized.
That's good. Another follow-up question, like you mentioned that like the processors, and then even if we will introduce a new processor, then it is able to communicate, or like it is able to connect with other processors. So it means that like we have some sort of predefined interface which
Yes, exactly.
which is like standard there.
Yes, that's right.
Sounds good. And another question, like it might not be too much relevant, but like probably it's always like just like a question which I have in my mind, but like not so sure like what is the best possible answer. You mentioned your experience in the gaming industry also. You mentioned that like you were debugging there. So often in the games we have the chat room there. So but like when I see the chat applications, then often there is a thing like they use separate protocols as not like standard protocols. And the reason for this is like there are some kind of real-time events involved, and then you have to wait for the messages to come. For example, in the JavaScript, we use the sockets.io library to implement that functionality. So I always like just gets curious like why we need to go for such kind of protocols. Why cannot we just use as some sort of events interface, like we publish an event and then we have a listener on the other end, we just listen it and that's it. Like just kind of like a trigger push and pull, which you were showing, like we push an event and on the other end we just have a pull of the event. So why the messaging thing cannot be simpler as that thing?
Yeah, that's a good question. I'm not a specialist of this part of video games, so my answer will be very generic. But I would tend to say that it is probably possible to operate in the way you described, because this kind of publish subscribe model, we even have libraries like RabbitMQ and other systems where you just register to a source of data and you get notified when something happens. And as a matter of fact, one of the extensions that we would like to develop for BeepBeep is something where a source processor is just, it registers on the RabbitMQ source of data and then it pushes events to down a BeepBeep pipeline. So it could be possible to connect these two things together. But I don't see why it couldn't be done that way, honestly.
Yeah. So well, probably they might have their own reasons, but like
yeah, but I don't know them.
yeah, that's it. So that's why I mentioned in the earlier, like it might be a little irrelevant question. So, but thank you so much for your feedback. Really appreciate that, and thank you so much for all those answers too.
Yeah, thank you for your questions.
Yeah, I know we're out of time, but I just maybe one thought that I had that I'd like to hear your opinion on. I know one of the things you mentioned with BeepBeep, it's really nice and lightweight. It can be deployed on like Raspberry Pis or IoT devices. One thing I was wondering that maybe you could use BeepBeep for, and it maybe goes back to the video games as one of the use cases. If you were to use BeepBeep and an AI model to learn from those event streams and try to predict upcoming events or events that will occur if we keep doing these particular sets of events, and then from that try to predict what maybe a correction event could be so we don't reach that undesirable outcome. Have you looked into applications such as that?
Yes, we did something a couple of years ago on what we called anomaly detection and forecasting. And it was working precisely in that way, that you first train a classifier on, for one of the examples where you train a classifier on a set of event streams, And then you use this classifier as a kind of in a predictive way after that. You have a processor that takes the classifier, the learned classifier, and then when it sees an event stream, it says, okay, there's 80% probability, then the next event will be this one. So we use pre-existing models. So it was not something we did that was an AI work, but we just showed how we could plug these things into a pipeline. So we have a journal paper that was published in 2019, if I recall, that is called Detecting Trend Deviations and Predictive Analytics, something like that. And it shows it's really basic what we do as a form of learning, but it's something that goes in the lines of what you're saying.
Yeah, perfect. Yeah, and I think I just found that paper as well, so I'll definitely check that out. Yeah, thank you very much for the presentation. I really enjoyed it, and thank you to the audience for asking your questions. All right, we will conclude.
Thank you.